I'm sorry for the delay. Let's get started here. I had planned way too much stuff for today, and so I've decided I'm taking section 4 off of the test. So even though it's written on the board, we're not going to do section 4 for the test. So colligative properties off the table. So chapter 10, sections 1 and 2 of chapter 11, and possibly molecular orbital theory. It'll kind of depend on if I think the test is too long, I'll take molecular orbital theory off of the test. Most of you did pretty fine on that on the quiz, so I don't think that should be problematic. Okay, yes. Yeah, we will stop at 11.2, no 11.4, and then 11.3 was never on the table, so. Okay, all right, and then don't forget you have a homework assignment due tomorrow night. I have not posted a homework that is related to chapter 11, so what I'm going to do is I'm going to create a practice related to chapter 11. So it's not an assignment, you don't have to stress about getting it done, but it'll be an opportunity for you to try out some of the things that are in chapter 11. All right, so the plan for today is to go over the details from sections 1 and 2, and then to hand back your quiz, go over your quiz, and I will probably go over a couple of things that are, I don't know where my brain is today. I will go over a couple of things that I didn't get a chance to put onto the quiz. So that is the plan for today. All right, so we were looking at solvation, which means dissolving stuff. And so when we have a solute or solvent molecules, in this case water, we surround the ions. And when they are when the solute is either polar or ionic, we get an orientation of the water molecules to face the charge or partial charge of that particular particle. So we see that for the potassium, because it's positive, we have the red oxygens facing inwards, and then for the negative chlorine, we have the white positive, partially positive hydrogens pointing in. If this were a polar molecule, we would just see the side of the molecule. Let's say methanol, the oxygen side is more negative. So the hydrogens on water would face towards the oxygen on methanol. And then the carbon side then is more positive. And so the oxygens would face the carbon side. So we see that kind of orientation there. We need to remember that there were 3 steps to our dissolving process. One step is separating each of the solute particles. So the lattice energy of this separating the ions from one another, or the dissociation energy of the water molecules separating them, because we've got to make room to fit the other molecules in. And so our third step is the mixing of those. And whether something is exothermic or endothermic is going to depend on whether we have a greater amount of gain in energy from mixing those things together, really strong attraction from mixing those things together, or if the energy to separate the molecules is greater. And then we also were talking about entropy, where we said entropy kind of plays a factor because the universe doesn't like things to get more organized. But when we have ions in particular, water molecules or polar solvent molecules are going to start orienting themselves in a more organized fashion around those particles. Okay. So we can imagine that if we replace this +1 charge with a +2, there's going to be a stronger attraction, and there's also going to be more organization, right? Because we're going to have more layers of the water that are still going to feel that positive pull from, say, a calcium 2+ than from the potassium 1+. So one thing that we talk about is charge density. So density is mass over volume, right? Charge density is charge over volume. So if the charge goes up, the charge density goes up, or if the size goes down, the charge density goes up, okay? And what happens with our ions as they become more and more charged? Well, they get smaller and smaller and smaller. So we have a higher charge on top and a smaller volume on the bottom. And so both of those are going to make for a higher charge density. So things that have a high charge density really attract water molecules around them, okay? And so those are the ions that we often see pick up a lot of water in lab, where we see waters of hydration. You might remember last semester we had the magnesium sulfate. We heated it up to drive off the water and see how much water was there. So a lot of the compounds that we work with have waters that are incorporated into the crystal, and that happens more often when we have a +2 charge than with a +1 charge because of that high charge density. I'm going to skip over this slide and go to this one. Okay, so these are energy diagrams kind of comparing the energy of separating our individual solvent and solutes with mixing them together. And in the first case, or in these cases, they only show one of them. They're kind of combining both the energy of separating the ions, the lattice energy, and the energy of separating the water molecules, the dissociation energy from those. So they are put together. You'll see 2 delta H's on each of these lines. And so in the first case, on the far left, we have sodium chloride, and the pink box is sitting on the left on the starting point, okay? And then it goes up in energy to separate everything, and then comes down in energy to mix them together. And so on the right-hand side, the blue box is sitting on the final situation. And so the fatter arrow is showing us overall what happened. So we have this moving slightly upward. So we don't notice a lot with sodium chloride. There's not a big change in energy, but there's a little one. So is that little one endothermic or exothermic? How do we think about that? Well, enthalpy is what we're measuring on the side. Remember, enthalpy is H. And so the change from initial to final is going to be delta H, right? And if it goes up, then delta H is positive. Okay, so thinking back to chapter 5 last semester, if delta H is positive or Q is positive, is it endothermic or exothermic? Endothermic. All right, so slightly endothermic, and we find this with most salts, and so we typically will think of things as behaving endothermically, and we'll see why that is something that relates to our intuition in just a minute. Okay, if we are looking at the middle one, the line in the middle is our starting point. So that's where we have sodium hydroxide. You've used that in lab, sodium hydroxide. And we have kind of a smaller arrow going up, okay? So that one is not so difficult to separate, to dissolve, to separate the ions, but we get a lot of energy back from dissolving, okay? So that we have that hydroxide ion that mixes very well with the water, and so we got a lot of energy out there. We also got a little bit of a chemical reaction going on there with neutralization. We're going to set that aside. And so overall, the fatter, darker arrow here is our overall energy, and it's going down. Okay, so delta H is negative. What does that tell us? Endothermic or exothermic? Exothermic. Okay. So what would we notice in lab when we mixed together sodium hydroxide and water? If it's exothermic, what would we notice? Do you remember when we did our calorimetry labs and we had the styrofoam cups? Most of the reactions that we looked at were exothermic. Most of them gave off heat. So this means heat is exiting the system and coming out to us, which is the surroundings. Okay, so it would feel warm to us. And then our last example is ammonium nitrate, which was the chemical that was in the coal pack that we had the picture of last week. And so in order to be cold, we have to have a lot of energy to separate the ions, but not much gain from mixing them back together again. And so the arrow points up, and this is endothermic. Okay. So for ions, they can kind of be all over the place. So I can't necessarily look at a formula and predict, is this going to be exothermic or endothermic? Now, if you're familiar with these and you do a lot of work with the ions, you get used to some patterns. But for our purposes, there's just not an easy way to predict it. So just know that sometimes it's endothermic, sometimes it's exothermic. So I want to take a second to look over here at what endothermic and exothermic tell us about, here we go, what it tells us about the temperature. So if I have something that is endothermic, that means delta H of dissolving it is going to be greater than 0 or positive. Then this is something that putting heat into it helps it to dissolve. And if putting heat into it helps it to dissolve, if I raise the temperature, it's going to dissolve better. So this is what I was saying. This is what we typically think of as being the case. If something doesn't dissolve well at room temperature, put it on a hot plate. If I want to dissolve more sugar in my water, I heat it up. So many, many things that we think of dissolving dissolve much better at higher temperatures. So after spring break, you're going to be doing a lab where you're going to be looking at the solubility of a salt at different temperatures. And you're going to see that for that salt, the higher the temperature, the more you will be able to dissolve. But if I take something like calcium chloride, which is exothermic, puts off heat, that means that heat is really driving the reverse reaction, causing it to become more solidified. And so higher temperatures actually make it less soluble. So when delta H is negative, then it is less soluble at high temperatures. Okay, so that's not typically the case. This does have an advantage for things like calcium chloride, though. If you think about rock salt that you might put on the roads during the winter, that salt is going to give off heat if it is calcium chloride, which in turn is going to help melt things. So we have kind of that dual action going there. But we'll get to colligative properties after the test. All right. So I'm going to share this again. Okay. All right, so what's going on in these pictures? In these pictures, we have not ions and water, but rather we have a solvent that is hexane. So hexane is mostly carbon and hydrogen. It's all carbon and hydrogen. Anybody remember for carbon and hydrogen together what the dominant interparticle force is? Dispersion. So if that's not something you know off the top of your head, it might be something to put on your 3x5 note card for your exam on Wednesday. All right, and then okay, so that is our solvent. And so since the dispersion forces are weaker, there's not a lot of energy to separate the hexane. So we see a very small arrow here to separate the hexane. If I try to dissolve salt in this, we normally wouldn't think of being able to dissolve ionic things in something that only has dispersion forces. But if we tried to, we would find that there's a whole lot of energy that goes into separating the ions from one another compared to the hexane. And so our second error there is really big. Then the energy we get from mixing them together, the attraction between the salt and the hexane is very small. They really aren't attracted to each other. So I've just got a teeny tiny mixing arrow going back down. And so my overall energy change is very, what, endothermic or exothermic? Endothermic. So much so that it is very, very difficult to dissolve salt in hexane. So just a teeny tiny bit that right next to those ions will get a little bit of dissolving, but other than that, not really much going on. Now, in contrast, if I take hexane and mix it with octane, hexane is 6 carbons, octane is 8 carbons. Both of them have what kind of forces? Dispersion. And I gave you the hint there. So neither one of them has a very big delta H to separate. I don't get a whole lot of energy back from mixing them, but it's enough to make this very slightly exothermic. Okay. All right. What about gases? So most gases that we might think about, nitrogen is N2, oxygen is O2, argon is just an atom. What kind of forces are we looking at there? Dispersion, because they're all non-polar. Okay. So when we dissolve those, it doesn't take much energy to separate them. But when we dissolve them, we're taking something that's very spread out and combining it to a small space. Okay. And in that small space, it has lots less freedom of motion. So delta S, S is our entropy. You don't remember delta S. Delta S is entropy or randomness. That's going to be negative because it's becoming more organized and less random. And does the universe like it when we organize things? Not really, because it requires energy to organize things. So if we're going to dissolve a gas, in order for that to happen, we have to fight against that negative delta S. And the way we're going to fight against it is to make delta H very, very negative. So very exothermic. So for all gases, delta H is very negative. So we said with ions, it can kind of go either way. But for gases, delta H is very negative. All right, so I gave you a couple of test tubes. One of the test tubes just has water in it, and one of the test tubes has a salt in it. So probably the easiest thing to do is pour the water into the salt and kind of shake it a little bit. Don't need to make a mess. And then feel the bottom of the test tube to determine has it gotten hotter or cooler. Okay, so if your test tube got hotter, you had calcium chloride, that was exothermic. And if you had one that got colder, you had ammonium nitrate. Okay, that was endothermic. All right, let's see. Some vocabulary. We talked about equilibrium. We talked about saturation in your vocabulary. So saturation is the maximum amount that you can dissolve of a particular substance in a particular solute. Depends on temperature. Saturated equilibrium applies when we have saturated solutions and a little bit of excess solute. What equilibrium means is I have both processes happening at the same time. In one direction, some of the solute is constantly dissolving. But the reason why I always have a little bit that's not dissolved is that since I'm at a saturation point, if I dissolve some, I have to precipitate out some others. So some of the solute is constantly precipitated. So you may have in your test tube a little bit of your, the calcium chloride tends to be the one that there's a little bit left of. You have a saturated solution in your test tube. Right at the interface of the two of them, some of the calcium and chlorine ions are getting together and forming crystals, and at the same time, some of the crystals that are near that water are dissolving. And the effect is the concentration never changes. We're always right at saturation. So we'll talk about equilibrium quite a bit later in the semester. I like to give the example of when my daughter was a toddler. She liked to take videotapes off of the shelf and just put them on the floor. Videotapes are what we had before DVDs and Blu-ray and everything streaming. And so she put them on the ground, but we didn't want to pick up a huge mess later. So, you know, we just sit there and put them back on the shelf, and she'd pull them off and we put them back. And so the result was there was always about 2 or 3 videotapes on the floor, but it was never the same videotapes. Okay, so the two processes, her pulling them off and us putting them back, those are opposite processes, were happening at the same time and the same rate. So that's what was equal, is how fast we were doing those things. But the concentration or the number of videotapes on the ground stayed the same. Okay, so we'll come back to this idea of equilibrium several times during the semester. All right, so next thing we're going to talk about is electrolytes. We're going to focus mostly on ionic solutes. So electrolytes form ions when dissolved. They're substances that dissolve in water and undergo a physical or chemical change to produce ions. So basically, they dissolve to form ions. So we normally can recognize these because they tend to be ionic compounds. Non-electrolytes are substances that don't produce ions in water, so covalent compounds. So you might think to yourself, well, water is a covalent compound. It's not ionic, but I've been told I'm not supposed to swim in water when there is an electrical storm outside. Okay, so let's try this out. So this is a light bulb that has, I'm not going to touch it right now, this way. Okay, so you guys at home are looking at this light bulb here. Okay, there are 2 probes coming out of the bottom. If I were to connect those probes, I would get a light. So right now it's turned off. I'm going to turn it on. No light. So I have this that is metal. I'm going to hold on to the wooden part so I don't hurt myself. And if I lay it across these 2 probes, voila, let there be light. Okay. So what I'm going to try and do is find a way to connect those 2 things using a solution. And so I have, oh gosh, did I mix them up? This one. This is distilled water or deionized water. So deionized means there should be no ions in here. It's just water. And so if I put this in here, not much happens. Not very interesting. Now, if I take, this one has salt in it. I can light that up. Okay. And I could just, where's my salt shaker? I could do the same thing with this one. So remember, this is the one that doesn't light up. Okay. Just put a little bit of salt in there, not too much. Stir it up, doesn't take much. I didn't get a whole lot in. So the less I have in there, the less bright it is. And so when it was very concentrated, I had a whole bunch. So what happens if I have something that is covalent but not an electrolyte? So this one has sugar in it. I don't have another, oh, I do have another sugar. Okay, so we can see, not doing much right here. I'm gonna put some sugar in here. Mix it up just like I did with the salt. There was even more of this than there was the salt. And still not. Okay. So non-electrolyte, and I can recognize this by the formula because sugar has carbon, oxygen, hydrogen. No metals, it's not ionic. Okay. Sodium chloride is ionic. Now, if I take this, I'm gonna rinse this out a little bit and use tap water, we might think about what's the difference between the water in the lab and the water when you go swimming in a lake or a pool. Well, in the environment, water always has some kinds of ions. There's salt everywhere. In your pool, you're going to put some chlorine of some kind. And so when I put this in here, it might at first look like there's not much going on. Oh, it's just barely there. I'm gonna have to turn off the light for you guys to see. Wait a second. You see the tiny little glow there? All right. So there is just a little bit of glow there because there are very, very few ions in there, but there are some. Okay. So we can conduct electricity in the swimming pool or whatever. And that's why your parents told you not to go swimming when it's thunderstorm. You can go swimming in it if it's not thunderstorm, provided you know how to swim and you haven't just eaten. But that's a story for another. Okay, so let's go back to our PowerPoint. As we are learning in chemistry, things are very rarely all one thing or another. That's the one, that's the one. So we also have weak electrolytes. So weak electrolytes are not the same thing as not concentrated. The weak electrolytes are things that are mostly covalent, but they'll release a few ions. And so what that might mean is if I had 10,000 molecules, I might get 1 or 2 ions released. Okay, this might happen for a weak acid. So vinegar, for example. If I were to do the same test with the vinegar, it would behave kind of like the tap water or the not concentrated salt, because even though the vinegar is very concentrated, it just doesn't have very many ions because so few percentage-wise dissociate. So a relatively small fraction of those dissolved substances generates ions. And you should put with this, as an example, weak acids. Okay, that's our best example of weak electrolytes. All right, another vocabulary term, miscible. When we have 2 materials that can mix together in any ratio, any proportion, we call them miscible. So gases are miscible because they're not touching one another. So I can mix them in any ratio. I can have a lot of oxygen and a little bit of chlorine. I can have a whole bunch of nitrogen and a little bit of oxygen. They are miscible, or we say infinitely miscible. So good examples would be some kind of alcohol and water. So ethanol or methanol, both of those have hydrogen bonding. And so does water. And they're small molecules. So is water. So it doesn't matter what ratio I put them in. I can have just a splash of alcohol and a whole bunch of water. I can have a whole bunch of alcohol and just a splash of water. They will all mix together. So they are miscible. So miscible happens when you have the same intermolecular forces, okay? So our bottom example must have the same intermolecular force. So gasoline and oil, any idea what the same dominant intermolecular force is there? Okay, so gasoline and oil are almost entirely carbon and hydrogen. Dispersion forces, yes, okay. So I can take mineral oil, cooking oil, whatever, any kind of vegetable oil, that kind of thing. I can mix those in any ratio. I can also mix them with gasoline in any ratio. Doesn't matter how much I have of which, because they have the same forces holding them together. So in contrast, if I put two things together that have very, very different intermolecular forces, then I would say they are immiscible. So are you guys ready for the next slide? Okay, so immiscible liquids do not mix pretty much at all. So right where the two meet, just like with the salt and the oil, right where the two meet, there's going to be a tiny bit of mixing. So basically, they don't mix at all. They don't mix to an appreciable extent. And so we have an example of oil and water. Three minutes according to my watch. I do want to go over a couple of things that were not on the quiz. So I said I was going to go through some examples of main intermolecular forces that are on in mixtures. So if I had, let's say, CO2 and water, first thing I do is name the intermolecular force for each. Now, if I have something like this and I'm not sure, it's best to draw the dot structure. And what am I looking for on the dot structure to know if it's polar? Lone pairs. So there are no lone pairs on here. So this is dispersion. And then what is water? Hydrogen bond. Okay. I'm going to list my strongest force first. So hydrogen bonding is stronger than dispersion. So I'm going to swap places. And I'm also going to change names. Okay. Now ions get to stay the same. Dipoles get to stay the same. But what happens to dispersion? What do I change that to? Induced dipole. And then since water can't hydrogen bond with something that doesn't have hydrogen bonding, what is this going to do? Or I change hydrogen bond. Right. Okay, so if that's something that you're struggling with, you might take that list of things that we went through the other day and put that on your note card. Remember, you can use a note card. So this force would be dipole induced dipole. Now, what I commonly will do is I will say, let's take four substances. So I might take CO2, CH3OH, FeCl3, and CHCl3. Ask you for each of those. Okay, we've gone through most of these. This is dispersion. This one is hydrogen bonding. This one's ions. This one is dipole. And then after you've said what the individual substance size is, then I would say, what if I mix each of these in water? And so then you would say, okay, with carbon dioxide, it's dipole induced dipole. With hydrogen bonding, keep the name the same, hydrogen bonding. With ion, keep ion the same, but hydrogen bonding becomes dipole. And then if I have a dipole, then hydrogen bonding becomes dipole. Okay, so look through old tests, you'll see questions very similar. I might also ask you of these four, now that we know their forces, so we have dispersion, H bond, ion, and dipole, which has the highest melting point? So then we need to know what the strongest force is. Ion, ion. So you would say this is the strongest or the highest melting point, also the highest boiling point. Which one would have the highest vapor pressure? The vapor pressure goes in the other direction. So that one's going to be our dispersion. Right? At room temperature, carbon dioxide is all vapor. Okay? So I didn't get to ask those kinds of questions on the quiz. I just wanted to go through it. You must have Good luck.